Beneath Jupiter's ancient surface, hidden under a frozen shell thicker than Earth's tallest mountains, lies an ocean containing more water than all of Earth's seas combined. This isn't speculation, it's measured fact. Ganymede, the largest moon in our solar system, harbors a secret that transforms everything we thought we knew about where life might exist beyond Earth. In 1610, Galileo pointed his primitive telescope toward Jupiter and discovered 4 bright points of light orbiting the giant planet. He had no idea one of them contained an ocean. For centuries later, we've sent spacecraft past Ganymede, mapped its magnetic field, and measured its gravitational pull with extreme precision. The data tells an astonishing story. Deep beneath ice that would crush any submarine we've ever built, liquid water moves in currents we're only beginning to understand. Ganymede is massive. At 5,268 kilometers across, it's larger than Mercury. If it orbited the Sun instead of Jupiter, we'd call it a planet without hesitation. But size alone doesn't make it remarkable. What matters is the structure we've detected beneath that scarred, ancient surface. Layer upon layer of ice and water, stacked like a cosmic sandwich, each zone distinct in temperature, pressure, and composition. The surface ice isn't uniform. Roughly 40% is ancient, dark terrain covered in impact craters that have accumulated over billions of years. The rest is younger, brighter, scored with grooves and ridges that reveal a violent tectonic past. Something powerful resurfaced large portions of Ganymede, and that something came from within. The ice didn't just crack. It moved. Plates shifted. Entire regions were rebuilt by forces we're still trying to explain. Scientists first suspected an ocean in the 1970s, but suspicion isn't proof. The breakthrough came from Galileo, the spacecraft, not the astronomer. Between 1995 and 2003, this robotic explorer made 6 close flybys of Ganymede, gathering magnetic field data that changed the game entirely. Ganymede generates its own magnetic field, the only moon in the solar system known to do so. That field interacts with Jupiter's powerful magnetosphere in ways that reveal what's hidden below. When Galileo's magnetometer detected variations in Ganymede's field, researchers noticed something unexpected. The patterns suggested electrical currents flowing beneath the surface. Salty water conducts electricity. Pure ice does not. The data pointed unmistakably toward a subsurface ocean rich in dissolved salts. Multiple independent studies confirmed it. Ganymede has liquid water, and lots of it. How much water are we talking about? Conservative estimates suggest the ocean contains more water than Earth's Atlantic, Pacific, Indian, Arctic, and Southern oceans combined. Some models push that figure even higher. The ocean might be 100 kilometers deep, possibly more, sandwiched between layers of ice in a configuration nothing like what we see on Earth. Temperature becomes strange at those depths. Near the surface, ice reaches temperatures around -160 degrees Celsius, cold enough to shatter steel. But pressure changes everything as you descend. The weight of overlying ice creates heat through compression. Radioactive decay in Ganymede's rocky core adds more warmth. Tidal flexing from Jupiter's gravity generates additional energy as the moon's shape distorts slightly during its orbit. All these factors combine to keep water liquid despite being farther from the Sun than any ocean in our immediate cosmic neighborhood. The structure is layered in ways that challenge our understanding of planetary interiors. Scientists propose multiple distinct zones. The top layer is solid ice, perhaps 150 kilometers thick. Below that, the ocean. Beneath the ocean, another ice layer, but this ice forms under such extreme pressure that it becomes Ice 3, Ice V, or even Ice 6, exotic crystalline structures that only exist under conditions we can barely replicate in laboratories. These high-pressure ices are denser than water, so they sink, creating an inverted world where ice floats below liquid, not above it. At the very bottom sits Ganymede's rocky core, probably similar in composition to Earth's mantle but much smaller. This core might still be warm enough to drive hydrothermal activity. On Earth, hydrothermal vents pump minerals and heat into the deep ocean, creating oases of life in absolute darkness. Could similar processes operate on Ganymede? We don't know. But the possibility exists. Jupiter's influence on Ganymede cannot be overstated. The planet's gravity doesn't just hold the moon in orbit. It squeezes it. Ganymede's orbit isn't perfectly circular, so the strength of Jupiter's gravitational pull varies throughout each 7-day orbit. This variation flexes Ganymede's interior like a stress ball being repeatedly squeezed and released. That flexing generates heat, the same process that powers Io's spectacular volcanism and maintains Europa's subsurface ocean. But Ganymede's tidal heating is gentler than Europa's. Europa orbits closer to Jupiter and experiences far more intense flexing. Ganymede sits farther out, in a more stable orbit, receiving just enough tidal energy to maintain liquid water without the violent geological activity that resurfaces Europa constantly. This might actually be an advantage. A calmer environment could be more conducive to complex chemistry, perhaps even biology. The magnetic field discovery revealed something else. Ganymede's field is surprisingly strong, about 1% the strength of Earth's field. That might not sound impressive, but for a moon, it's extraordinary. The field originates from a metallic core, probably iron or iron-nickel, that remains partially molten. A dynamo operates inside Ganymede, circulating liquid metal and generating magnetism through the same basic process that protects Earth from solar radiation. This magnetic field creates a miniature magnetosphere around Ganymede, a protective bubble carved out of Jupiter's much larger magnetic environment. When Ganymede passes through different regions of Jupiter's magnetosphere, the interaction changes. Scientists use these variations to probe what lies beneath the ice. The ocean's salty water conducts electrical currents that alter the magnetic field in detectable ways. It's like using magnetism to see through hundreds of kilometers of ice without drilling a single hole. The composition of that ocean remains uncertain. We know it contains dissolved salts, but which salts? Sodium chloride, like Earth's oceans? Magnesium sulfate? Some exotic mixture we've never encountered? Spectroscopic observations of Ganymede's surface show evidence of various salts and minerals, including what might be hydrated salts pushed up from below through cracks in the ice. These surface deposits offer tantalizing clues about the ocean's chemistry, but they're just hints. We won't know the ocean's true composition until we sample it directly. Sampling that ocean presents extraordinary challenges. The ice shell is thicker than any ice we've drilled through on Earth. Antarctica's deepest ice cores reach about 3.5 kilometers. Ganymede's ice might be 50 times thicker. Drilling through that much ice would require technology we haven't developed yet, power sources that don't exist, and mission durations that stretch decades. Alternative approaches exist. Perhaps we could target thinner regions where the ice is fractured or where warm upwellings have thinned the shell. Maybe we could send a probe through one of the cracks visible on the surface, assuming those cracks penetrate deep enough. Or we might analyze material ejected from the subsurface by impacts or cryovolcanic activity. Each method has drawbacks, but they're being studied seriously. The surface itself tells stories about what lies beneath. Those parallel grooves and ridges covering the brighter terrain formed through tectonic processes. Ganymede's ice shell fractured and shifted, driven by forces from below. Some regions show evidence of past cryovolcanism, where liquid water or slushy ice erupted onto the surface, freezing instantly in the vacuum of space. These features are old, billions of years in some cases, but they prove the interior was once geologically active. The question is whether that activity continues today. Recent observations suggest it might. The Hubble Space Telescope detected evidence of water vapor plumes erupting from Ganymede's surface, similar to the plumes Enceladus shoots into space from its south polar region. If confirmed, these plumes would be game-changing. They'd provide direct samples of subsurface material without requiring us to land or drill. A spacecraft could fly through the plumes, collect particles, and analyze their composition. We'd learn about the ocean's chemistry, search for organic molecules, and potentially detect signs of biological activity, all without touching the surface. The plume evidence isn't conclusive yet. The signal is subtle, and alternative explanations exist. But if Ganymede does have active plumes, it joins Europa and Enceladus in a select group of ocean worlds that occasionally expose their hidden seas to space. This would make Ganymede a prime target for future missions designed to search for life beyond Earth. Understanding Ganymede's ocean requires understanding its history. The Moon formed roughly 4.5 billion years ago from the disk of gas and dust surrounding the infant Jupiter. Early in its history, Ganymede was probably much warmer. Radioactive decay and impact heating from late-stage bombardment would have created conditions warm enough to melt ice throughout the interior. The Moon might have been entirely liquid at some point, with a global magma ocean overlying a water ocean of staggering depth. As Ganymede cooled, it differentiated. Heavier rocky material sank to form the core. Lighter ices rose toward the surface. Water separated from rock, creating distinct layers. The cooling continued, but never reached the point where the entire Moon froze solid. Tidal heating from Jupiter and residual heat from radioactive decay kept the interior warm enough to maintain liquid water, even as the surface froze into the icy shell we observe today. That surface has been modified countless times. The dark, cratered terrain preserves Ganymede's ancient face, a record of impacts stretching back billions of years. The bright, grooved terrain is younger, perhaps 1 to 2 billion years old, created when the ice shell fractured and new ice flooded the surface. What triggered this resurfacing event? Possibly a period of enhanced tidal heating when Ganymede's orbit shifted slightly. Or perhaps a massive impact disturbed the ice shell enough to trigger widespread tectonic activity. The grooves themselves are puzzling. They run parallel for hundreds of kilometers, creating patterns that suggest systematic stress across the entire ice shell. Some researchers think the grooves formed as the ice expanded during freezing, creating tension that cracked the surface. Others propose they're the result of tectonic plates sliding past each other, similar to transform faults on Earth. The truth might involve both processes working together in ways we don't yet understand. What makes Ganymede's ocean potentially habitable? 3 factors stand out. First, liquid water, the universal solvent necessary for chemistry as we know it. Second, chemical energy sources, possibly including hydrothermal vents if the rocky core remains active. Third, time, billions of years for complex chemistry to evolve and potentially produce something we'd recognize as life. That third factor is crucial. Life on Earth didn't appear overnight. It took hundreds of millions of years for chemistry to cross the threshold into biology. Ganymede's ocean has existed for most of the solar system's history. If conditions have remained stable, that's an enormous window for biological processes to develop. Of course, stability doesn't guarantee life. It only provides the opportunity. Earth's ocean spent billions of years churning with chemistry before producing the first cells. And even after life emerged, it remained simple for most of Earth's history. Complex organisms, the kind that build structures or move purposefully, arrived remarkably late. On Ganymede, we're searching for something far more modest, evidence that chemistry has become organized, that molecules have learned to replicate, that energy flows through systems we could call metabolic. The search faces immediate obstacles. Ganymede's ocean lies beneath potentially 150 kilometers of ice. No drill exists that could penetrate that depth in reasonable time. No submarine could reach those depths and return data. We're forced into indirect methods, analyzing the surface for clues about what lies below, studying how the magnetic field behaves, watching for changes that might indicate activity deep within. But there's a faster approach. If Ganymede truly has water plumes erupting through the ice, we bypass the barrier entirely. A spacecraft flying through those plumes would sample ocean material directly. Instruments could detect organic molecules, measure salinity, identify chemical signatures that might indicate biological processes. We'd essentially be tasting Ganymede's ocean without ever landing. NASA and ESA are already planning missions that could make this happen. The Europa Clipper, launching in the 2020s, will study Jupiter's moons during multiple flybys. While its primary target is Europa, it will also observe Ganymede, searching for plume activity and mapping the magnetic field in greater detail. The JUICE mission, led by ESA, will spend years studying Ganymede specifically, eventually entering orbit around the Moon itself. JUICE carries instruments designed to peer through the ice using radar, to measure the thickness of different layers, to map variations in the gravitational field that might reveal ocean currents below. These missions won't answer every question. They're reconnaissance, not final proof. But they'll narrow the possibilities. They'll tell us where the ice is thinnest, where tidal heating concentrates, where future landers should aim. They're setting the stage for something more ambitious, a mission that actually touches Ganymede's surface and drills into the ice. Drilling on Ganymede presents challenges Earth's polar expeditions never faced. Temperatures hover around -160 degrees Celsius. There's no atmosphere to provide pressure or distribute heat. Solar power is weak this far from the sun. Any drill would need to carry its own energy source, probably a radioisotope generator, and melt through ice that's harder than concrete at those temperatures. The drill would need to operate autonomously, without real-time control from Earth. Radio signals take 40 minutes to travel between Jupiter and our planet, making remote piloting impossible. Every decision, every adjustment, would need to happen on site, guided by artificial intelligence capable of responding to unexpected conditions. Assuming we overcome those obstacles, what happens when the drill reaches liquid water? The bit punches through the final meters of ice and suddenly encounters resistance-free fluid. Sensors detect the transition. The drill stops advancing. A probe deploys, a small autonomous vehicle designed to separate from the drill string and swim freely in the ocean below. It carries cameras, though visible light penetrates only meters in these dark waters. It carries chemical sensors to taste the ocean's composition. It carries sonar to map the underside of the ice and detect objects in the surrounding water. And it carries life detection instruments, devices designed to recognize patterns that biology creates, organic molecules arranged in ways chemistry alone wouldn't produce. This isn't science fiction. Engineers have already built prototypes. They've tested autonomous underwater vehicles beneath Antarctic ice, demonstrating that machines can navigate and collect samples in environments humans will never visit. The technology exists. What's missing is the funding, the political will, and the decades of patience required to send these systems to another world. Why go to such extraordinary lengths? Because Ganymede represents a test case for a much larger question. If life can arise in an ocean sealed beneath ice, isolated from sunlight, dependent entirely on chemical energy from hydrothermal vents, then life might be common throughout the universe. Most planets don't orbit their stars in the narrow habitable zone where liquid water can exist on the surface. But countless moons orbit giant planets, experiencing tidal heating, maintaining subsurface oceans regardless of how far they are from their star. Ganymede-like worlds might outnumber Earth-like worlds by orders of magnitude. Finding life on Ganymede would fundamentally shift how we think about biology's place in the cosmos. It would suggest that wherever liquid water persists for geological time, life finds a way to emerge. The universe suddenly becomes much more alive, even if that life hides beneath frozen surfaces, invisible to telescopes, detectable only through patient exploration. The implications extend beyond biology. Ganymede's ocean, if inhabited, would represent a second origin of life in our solar system. Earth's life shares a common ancestor. Every organism, from bacteria to blue whales, descended from the same primordial cell. We're all one family, variations on a single theme. But life on Ganymede, if it exists, would have started independently. Its chemistry might use different molecules. Its cells might have different structures. Its metabolism might run on different reactions. Comparing Earth life to Ganymede life would reveal which aspects of biology are universal and which are accidents of our particular history. There's also the possibility that Ganymede's ocean contains nothing alive at all. That the chemistry never crossed the threshold, that the conditions weren't quite right, that life requires something we haven't identified yet. This outcome would be scientifically valuable too. It would tell us that liquid water and chemical energy aren't sufficient. That life requires additional factors we need to understand before we can predict where else it might arise. Every null result narrows the search, eliminating possibilities, focusing attention on what truly matters. Ganymede's future depends partly on Jupiter. The giant planet's gravity dominates the entire system. Tidal forces that keep Ganymede's ocean liquid also create stress throughout the Jovian system. Jupiter's moons interact gravitationally, their orbits shifting subtly over millions of years. These orbital changes affect how much tidal heating each moon experiences. Ganymede might be warming or cooling depending on these long-term cycles. The ocean could be expanding or contracting. The ice shell might be thickening or thinning. We're seeing a snapshot of a dynamic system, one that changes on timescales far longer than human civilization has existed. Looking billions of years forward, Ganymede's fate is tied to the Sun. Our star is slowly brightening. In roughly 1 billion years, it will be hot enough that Earth's oceans begin to evaporate. The habitable zone will shift outward. By the time the Sun becomes a red giant, perhaps 5 billion years from now, it will expand dramatically, possibly engulfing the inner planets entirely. Jupiter's orbit will be warm enough that Ganymede's ice shell melts completely. The Moon might briefly have a surface ocean, liquid water exposed to space, before the Sun's evolution continues and everything boils away. But that's distant speculation. Right now, Ganymede orbits Jupiter much as it has for billions of years. Its surface remains locked in frozen silence. Its ocean, if inhabited, contains life that has never seen a star, never experienced seasons, never known anything beyond the crushing pressure and absolute darkness of its submerged world. And yet, that life, if it exists, would be our cosmic cousin, proof that the universe creates biology wherever conditions allow, that we're not alone in finding ways to persist and adapt and thrive. The next steps are clear. We need to return to Ganymede with better instruments. We need to map the ice shell's thickness precisely. We need to confirm whether plumes are erupting. We need to identify the best drilling sites. And eventually, we need to send a drill, punch through that ice, and taste the ocean that has remained hidden since the solar system's birth. Each mission builds on the last. Each discovery raises new questions. The process is slow, frustratingly slow for those eager for answers. But it's also methodical, accumulating evidence piece by piece, building a case that will eventually become undeniable. Ganymede doesn't care whether we study it or not. The Moon will continue its orbit, its ocean will continue to slosh beneath the ice, its magnetic field will continue to deflect Jupiter's radiation. But we care, because understanding Ganymede means understanding how common habitable environments might be throughout the galaxy. It means learning whether life is a cosmic accident that happened once, here on Earth, or an inevitable consequence of chemistry given the right conditions and enough time. That question drives everything we do in space, every mission we plan, every instrument we build. Ganymede's story matters because it rewrites what we thought we knew about where life can exist. For most of human history, habitability meant one thing: being near a star at just the right distance. Not too hot, not too cold. The Goldilocks zone. Earth sits comfortably within that zone, receiving sunlight that keeps water liquid on the surface. That seemed like the requirement. No sunlight, no warmth, no life. Ganymede ignores that rule completely. It orbits 5 times farther from the Sun than Earth does. Sunlight there is faint, barely more than moonlight from our perspective. Surface temperatures hover around -160 degrees Celsius. By traditional standards, Ganymede should be a frozen wasteland, utterly sterile. Yet beneath that frozen exterior lies an ocean larger than all of Earth's oceans combined, kept liquid not by sunlight but by gravitational friction. The rules changed. Habitability no longer requires proximity to a star. It requires energy, and energy comes from multiple sources. This realization transforms how we think about the galaxy. Current estimates suggest hundreds of billions of planets exist in the Milky Way alone. Most orbit too far from their stars to have surface liquid water. We used to dismiss those worlds as uninteresting, too cold to matter. But if tidal heating can maintain subsurface oceans, then billions of frozen worlds suddenly become potential habitats. Ice becomes a protective shell rather than a barrier. Darkness becomes normal rather than fatal. The number of potentially habitable environments in the galaxy might be orders of magnitude higher than we previously calculated. Europa taught us this lesson first. It's smaller than Ganymede, closer to Jupiter, and experiences even more intense tidal heating. Its ice shell might be only 15 to 25 kilometers thick, potentially thin enough that drilling becomes realistic with current technology. Europa's ocean might be in direct contact with a rocky seafloor, creating conditions similar to Earth's hydrothermal vents. Those vents on Earth support ecosystems that thrive without sunlight, using chemical energy instead. If Europa has similar vents, it might have ecosystems too. But Ganymede offers something Europa doesn't: stability. Europa's surface is young, constantly resurfacing from geological activity. Its ice shell might be churning, cycling material between the surface and the ocean on relatively short timescales. That's good for delivering nutrients but chaotic for any life trying to establish itself. Ganymede's surface is ancient, some regions dating back billions of years. The ice shell appears thicker, more stable. The ocean beneath might be calmer, less disturbed. Life, if it exists, has had billions of years to develop in relatively stable conditions. That matters enormously. Consider Earth's history. Single-celled organisms appeared relatively quickly, within the first billion years after the planet cooled enough to have liquid water. But complex life took far longer. Multicellular organisms didn't emerge until roughly 600 million years ago. Large animals appeared only in the last half-billion years. Intelligence required even more time. Evolution isn't just about having the right ingredients. It needs time to experiment, to try countless variations, to stumble upon solutions that work. Ganymede has had that time. If its ocean formed during the solar system's early days, life there has had 4 billion years to evolve. What might 4 billion years of evolution produce in an alien ocean? We have no idea. That's the honest answer. Earth's oceans contain everything from microscopic bacteria to blue whales, from simple sponges to intelligent octopuses. Evolution explores countless paths, finding solutions we'd never imagine. An alien ocean isolated from Earth's evolutionary history would follow its own trajectory, shaped by different pressures, different chemistry, different constraints. The organisms there, if they exist, might share some basic principles with Earth life. They'd need to extract energy from their environment, maintain their internal chemistry, reproduce. But the details could be utterly foreign. Imagine organisms that navigate by sensing magnetic fields directly, creatures that communicate through electrical signals in ways far more sophisticated than Earth's electric fish. Perhaps something analogous to plants but using chemical energy from hydrothermal vents instead of sunlight, creating the base of a food chain. Predators that hunt in absolute darkness using senses we can't comprehend. Maybe colonial organisms, vast networks of interconnected cells functioning as single entities, stretching across kilometers of ocean floor. Or nothing like any of those things. Evolution is creative in ways that constantly surprise us even when studying Earth's own biosphere. The chemical composition of Ganymede's ocean adds another layer of complexity. Earth's oceans are salty, dominated by sodium chloride. Ganymede's ocean might have different salts, possibly magnesium sulfate or other compounds. The pH could be different. The pressure at the ocean floor would be immense, potentially several hundred times Earth's atmospheric pressure. Organisms there would need to function under those conditions. They'd have no concept of low pressure, no evolutionary history of dealing with anything but crushing weight. Bring them to the surface and they'd likely die instantly, cells rupturing from the pressure drop. We'd need to maintain samples at depth, study them in specialized chambers, never letting them experience what we consider normal conditions. Temperature poses another question. Earth's deep oceans are cold but not frozen, typically around 2 to 4 degrees Celsius. Ganymede's ocean temperature depends on how much heat reaches it. Near the ice shell, it's probably just above freezing, close to 0 Celsius. Near the ocean floor, if hydrothermal vents exist, temperatures could spike dramatically. Earth's vents can reach hundreds of degrees Celsius. Water remains liquid under pressure at those temperatures. Organisms on Earth thrive in these extreme environments. Ganymede might have similar temperature gradients, creating diverse habitats within the same ocean. Cold-adapted organisms near the ice, heat-loving extremophiles near vents, and everything in between. Salinity affects what can dissolve in water. Different salts change water's properties, how it conducts electricity, how it freezes, how molecules move through it. Life would adapt to whatever chemistry exists there, evolving proteins and cell membranes suited to that specific environment. We can't simply transplant Earth organisms to Ganymede's ocean and expect them to survive. The chemistry would be wrong. But native organisms, if they exist, would be perfectly suited to their home, finding our ocean as alien and hostile as we'd find theirs. Energy sources drive everything. On Earth, sunlight powers most ecosystems directly or indirectly. Remove the sun and Earth's biosphere would collapse within years. Ganymede never had that dependence. Its energy budget relies on tidal heating and possibly radioactive decay in the rocky core. That's a limited energy supply compared to sunlight. Earth receives roughly 174 petawatts of solar energy. Ganymede's tidal heating probably delivers far less, maybe a few terawatts at most. That limits how much biomass the ocean can support. An ecosystem there would be sparse compared to Earth's teeming oceans. Fewer organisms, spread over vast distances, competing for limited chemical energy. Life, but not abundant life. Survival, but on the edge. This scarcity might actually favor certain evolutionary paths. On Earth, competition drives arms races, predators evolving better hunting skills, prey evolving better defenses. But in energy-poor environments, cooperation sometimes wins over competition. Organisms might evolve symbiotic relationships, sharing resources, supporting each other's metabolism. We see this on Earth in extreme environments. Lichens are partnerships between fungi and algae. Deep-sea tube worms host bacteria that process chemicals from hydrothermal vents. Ganymede's organisms might take cooperation even further, creating integrated systems that blur the line between individual and colony. Then there's the question of complexity. Does low energy availability limit how complex organisms can become? Large brains require enormous energy. Human brains consume roughly 20% of our total energy budget despite being only 2% of our body mass. Intelligence is expensive. In Ganymede's ocean, that cost might be prohibitive. Evolution might favor simple, efficient organisms over complex, energy-hungry ones. Intelligence might never emerge, not because it's impossible but because it's not worth the energy investment. Or perhaps intelligence evolves differently there, taking forms that don't require massive energy consumption. Distributed intelligence across colonies, simple individual units that collectively make complex decisions. We assume intelligence looks like human brains. It doesn't have to. Time becomes fascinating when discussing Ganymede's potential biosphere. Earth's organisms evolved alongside a changing planet. Continents shifted, climates changed, ice ages came and went. Mass extinctions wiped out dominant species, allowing new lineages to emerge. Evolution responds to change. But Ganymede's ocean might be remarkably stable. No seasons, no day-night cycle, no continental drift affecting ocean currents. Temperature and chemistry might vary little over millions of years. In such stable conditions, evolution might slow. Once organisms adapt well to their environment, there's less pressure to change. We might find living fossils, organisms essentially unchanged for billions of years because their environment never demanded innovation. Or perhaps stability allows evolution to explore other directions. Without constant environmental upheaval, evolution might focus on optimization rather than adaptation. Organisms becoming incrementally more efficient at extracting energy, processing nutrients, reproducing. Refinement over time rather than dramatic shifts. The result would be organisms exquisitely tuned to their environment but unable to cope with even slight changes. Specialists rather than generalists. That creates vulnerability. If something disrupts Ganymede's ocean, a massive impact delivering heat, a change in Jupiter's tidal forces, the ecosystem might collapse entirely, unable to adapt quickly enough. We're speculating, building hypotheses from limited data. That's necessary at this stage. We can't know what exists on Ganymede until we look. But we can make educated guesses based on physics, chemistry, and biology. We can identify what's possible, what's probable, what's unlikely. Those guesses guide mission planning, helping us decide where to look, what instruments to bring, what measurements matter most. Every mission updates our understanding, confirms some guesses, disproves others, raises new questions we hadn't considered. Europa offers a different scenario, another frozen moon hiding an ocean, but with critical differences. It orbits closer to Jupiter than Ganymede, experiencing stronger tidal heating. That means more energy available for life, potentially more active geology on the ocean floor. Europa's ice shell might be thinner, perhaps only 10 to 15 kilometers in some regions. Thinner ice changes the game entirely. With less ice overhead, more radiation from Jupiter penetrates deeper. Radiation breaks apart water molecules at the surface, creating oxidants, chemicals that can participate in biological reactions. Some of those oxidants might work their way down through cracks and fractures, mixing into the ocean below. That influx represents a different energy source, one independent of hydrothermal vents. Earth's early oceans lacked oxygen for billions of years. Life evolved without it, using other chemical pathways. When photosynthetic organisms finally started producing oxygen, it changed everything, enabling more efficient metabolism, more complex organisms, larger bodies. Europa's ocean might skip the waiting period. Oxidants from the surface could provide that efficiency boost from the start, allowing life to evolve along different trajectories than Earth's early biosphere. Europa's surface shows strange features, reddish-brown streaks and patches staining the ice. Spectroscopy suggests those colors come from salts, sulfates, and organic compounds brought up from below. The ice isn't static. It churns, cycles, brings deep material to the surface, sends surface material down. That exchange creates possibilities. If life exists in Europa's ocean, evidence might reach the surface eventually, locked in ice we could sample without drilling through kilometers of frozen water. NASA's Europa Clipper mission, launching soon, will study those surface features in detail, mapping the ice shell's thickness, measuring the ocean's salinity, searching for plumes of water vapor erupting through cracks. The Hubble Space Telescope spotted potential plumes back in 2012 and 2016, geysers shooting water hundreds of kilometers above the surface. If those plumes are real and consistent, a spacecraft could fly through them, collecting samples directly from the subsurface ocean without landing. Analyzing those samples for organic molecules, for chemical signatures inconsistent with purely geological processes, for anything suggesting biological activity. That's the dream scenario, finding life without the engineering nightmare of drilling through ice in low gravity on a radiation-blasted moon. But plumes are unpredictable. They might not erupt when we're watching. They might not contain material from deep enough to include biological signatures. We might fly through them and find only water vapor and ice crystals, learning nothing about what lies below. Still, it's worth trying. The payoff, if successful, justifies the risk. Then there's Enceladus, Saturn's tiny moon, barely 500 kilometers across. Too small for significant radioactive heating, too far from Saturn for strong tidal forces. By all rights, it should be frozen solid, geologically dead. Yet it's not. In 2005, Cassini detected massive plumes erupting from cracks near Enceladus's south pole, shooting water vapor, ice particles, and organic molecules into space. Those plumes feed Saturn's E-ring, a faint ring of ice particles orbiting the planet. Enceladus is active, spectacularly so, despite having no obvious reason to be. The best explanation involves tidal heating, but in a subtle form. Enceladus orbits Saturn in resonance with other moons, gravitational interactions that slightly alter its orbit over time. Those orbital changes generate just enough tidal flexing to keep a subsurface ocean liquid, at least beneath the south polar region. The ocean might be relatively small, perhaps confined to a layer beneath the southern hemisphere rather than encircling the entire moon. But it's there, and it's in direct contact with space through those cracks, essentially offering free samples to any spacecraft passing by. Cassini flew through Enceladus's plumes multiple times, analyzing their composition. Water vapor, as expected. Salts, indicating the ocean is salty. Molecular hydrogen, suggesting hydrothermal activity on the ocean floor where hot water reacts with rock. Organic molecules, simple ones like methane, but also more complex carbon compounds. Everything needed for life, delivered directly into space where we can study it. We've already sampled Enceladus's ocean, at least partially. We just haven't analyzed the samples thoroughly enough yet. Future missions could do better. A dedicated Enceladus orbiter could fly through the plumes repeatedly, collecting particles, measuring their composition with high-precision instruments. We could search for amino acids, the building blocks of proteins. For lipids, which form cell membranes. For nucleotides, the components of DNA and RNA. For anything that screams biology rather than chemistry. Detection wouldn't be simple. Organic molecules exist in space independent of life. Meteorites contain amino acids formed through non-biological processes. We'd need to identify patterns, ratios of molecules, specific configurations that make sense only in biological contexts. Left-handed versus right-handed amino acids, for example. Life on Earth uses exclusively left-handed amino acids and proteins, even though both forms exist naturally. Finding a strong preference for one-handedness in Enceladus samples would raise serious questions. Or we could look for complexity. Random chemistry produces simple molecules. Biology produces complex ones, polymers, chains of repeating units with specific sequences. DNA is a polymer. So are proteins. Finding long-chain molecules with non-random sequences would be compelling evidence, not definitive proof, but enough to shift the conversation from "might life exist" to "how do we confirm it exists?" Titan, Saturn's largest moon, presents an entirely different puzzle. It's the only moon in the solar system with a thick atmosphere, denser than Earth's, composed primarily of nitrogen with a few percent methane. That methane shouldn't be there. Sunlight breaks methane apart, converting it to more complex hydrocarbons. Without a continuous source, Titan's atmospheric methane should disappear within tens of millions of years. Yet it's still there, suggesting active replenishment from Titan's interior. Titan's surface temperature hovers around -179 degrees Celsius, cold enough that water ice behaves like rock, hard and unyielding. Liquid water can't exist on the surface. But liquid methane can. Titan has lakes, rivers, and seas of liquid methane and ethane, a hydrological cycle running on hydrocarbons instead of water. Methane rains from clouds, flows across the surface, collects in basins, evaporates back into the atmosphere. It's alien yet strangely familiar. Could life exist in liquid methane? Water-based life seems impossible at those temperatures. Biochemistry as we know it relies on water's unique properties, its ability to dissolve many substances, its role in biological reactions. Methane doesn't share those properties. It's a poor solvent, doesn't participate in the same kinds of reactions. Life in methane lakes would require completely different chemistry, different molecular structures, different energy sources. Some scientists propose hypothetical organisms with cell membranes made from compounds that remain flexible at cryogenic temperatures, metabolisms based on reactions between hydrogen and acetylene rather than oxygen and glucose. These organisms would be slow, unimaginably slow, their chemistry proceeding at rates millions of times slower than Earth life. They might take centuries to reproduce, millennia to evolve noticeable changes. But slow doesn't mean impossible. Titan also hides a subsurface ocean, this one made of water mixed with ammonia, buried beneath an ice shell perhaps 100 kilometers thick. That ocean wouldn't host methane-based life, but conventional water-based organisms might thrive there, similar to what we expect on Europa or Enceladus. Titan could potentially host two completely separate biospheres, one in surface methane lakes, another in the deep water ocean, neither aware of the other's existence. Testing these ideas requires landing on Titan, sampling the lakes, analyzing their chemistry. NASA's Dragonfly mission, scheduled to launch in the 2030s, will do exactly that. It's a rotorcraft, essentially a drone, designed to fly through Titan's thick atmosphere, landing at multiple sites, collecting samples, searching for organic molecules and chemical patterns that might indicate biology. Finding life in Titan's methane lakes would revolutionize biology more than finding it on Europa. Europa's ocean resembles Earth's early seas closely enough that life there might operate on similar principles. Titan's surface environment has no Earth analog. Life there would represent a genuinely independent origin, proving that biology isn't limited to water, that the universe might harbor forms of life we haven't imagined yet. Mars complicates the discussion. It's not an ocean world now, but it was once. Billions of years ago, Mars had rivers, lakes, possibly even a northern ocean. Liquid water flowed across the surface under a thicker atmosphere. That Mars could have hosted life, might still host remnants of that ancient biosphere in subsurface aquifers or deep rock formations. Recent discoveries strengthen that possibility. Orbital radar detected what appears to be a large reservoir of liquid water beneath Mars's south polar ice cap, kept liquid by salts that lower water's freezing point. If confirmed, that reservoir could harbor microbial life, organisms surviving in isolation since Mars's surface dried out billions of years ago. Mars also shows seasonal variations in atmospheric methane, concentrations rising and falling in patterns that don't match simple geological explanations. On Earth, methane comes primarily from biological sources, produced by microorganisms in oxygen-poor environments. Martian methane could have biological origins, microbes living underground, releasing methane that seeps to the surface. Or it could come from geological processes, reactions between water and rock that happen to produce methane. We don't know yet. Distinguishing between biological and geological methane requires isotope analysis, measuring the ratios of different carbon isotopes in the methane molecules. Biological processes prefer lighter isotopes, creating characteristic ratios. Future Mars missions will carry instruments capable of that analysis, potentially answering whether Mars's methane hints at hidden life. Venus seems like a terrible candidate for life. Surface temperatures exceed 460 degrees Celsius, hot enough to melt lead. Atmospheric pressure at the surface equals that found nearly a kilometer underwater on Earth. The atmosphere is mostly carbon dioxide with clouds of sulfuric acid. Nothing lives there, surely. But Venus's upper atmosphere, 50 to 60 kilometers above the scorched surface, offers more hospitable conditions. Temperature and pressure there resemble Earth's surface. The clouds contain water droplets, though mixed with sulfuric acid. Some microorganisms on Earth, extremophiles living in acid mine drainage, tolerate similarly harsh chemistry. Could microbes drift through Venus's clouds, floating in the relatively mild upper atmosphere, avoiding the hellish surface below? In 2020, scientists detected phosphine in Venus's atmosphere, a gas that on Earth is produced almost exclusively by anaerobic microbes. Phosphine shouldn't persist in Venus's atmosphere, it should react with other compounds and break down quickly. Its presence suggests active production from some source. Biological production would explain it, though geological processes might also be responsible. The detection sparked intense debate, subsequent observations yielded conflicting results, and the question remains unresolved. Looking for life beyond Earth isn't just about finding microbes in ice or gas signatures in distant atmospheres. It's about understanding whether biology is common or rare, whether Earth represents a cosmic fluke or an inevitable outcome when conditions align. Every ocean world, every atmospheric anomaly, every unexplained chemical signature adds evidence to one side of that fundamental question. The search methods keep evolving. Early approaches assumed alien life would resemble Earth life closely, using the same chemistry, the same energy sources, the same molecular building blocks. Modern astrobiology thinks broader. Life might use different solvents, different genetic molecules, different metabolic pathways. Methane could replace water. Silicon might substitute for carbon. Genetic information could be stored in molecules we haven't considered. This flexibility makes detection harder but more interesting. Biosignatures, the signs life leaves behind, fall into several categories. Atmospheric biosignatures include gases that don't belong, oxygen accumulating where it shouldn't, methane appearing in suspicious patterns, phosphine showing up without clear geological sources. These gases react with other atmospheric compounds, breaking down over time. Their persistence means something keeps producing them. Surface biosignatures include patterns visible from space, regular seasonal changes in color suggesting vegetation cycles, reflectance spectra matching chlorophyll or similar pigments. Temporal biosignatures involve changes over time, day-night variations in atmospheric chemistry, seasonal fluctuations in gas concentrations, patterns that match biological rhythms rather than simple physics. Each type has limitations. Geology mimics biology frustratingly well. Volcanoes produce gases that resemble metabolic waste. Mineral reactions create compounds that look biological. Seasonal temperature changes drive chemical cycles that mirror life's rhythms. Distinguishing biology from geology requires multiple lines of evidence, combinations of signals that together become harder to explain without invoking life. The James Webb Space Telescope changed the game for atmospheric analysis. Its infrared instruments can detect molecular signatures in exoplanet atmospheres during transits, when planets pass in front of their stars. Starlight filters through the planet's atmosphere, certain wavelengths get absorbed by atmospheric molecules, and the resulting spectrum reveals what's present. Webb can detect water vapor, carbon dioxide, methane, ammonia, and more complex organic molecules. Finding oxygen and methane together would be significant. Those gases react with each other, so their coexistence suggests continuous production from some active source. But even that wouldn't prove life conclusively. Jupiter's moon Io has a thin oxygen atmosphere produced entirely by geological processes, radiation breaking apart water molecules frozen on the surface. Methane appears in many planetary atmospheres from purely chemical reactions. The combination becomes interesting, especially if accompanied by other biosignatures, seasonal variations, or unexplained ratios between different isotopes. Searching ocean worlds requires different strategies. We can't directly observe their buried seas. Instead, we look for indirect evidence, plumes of water vapor erupting through surface ice, chemical analysis of that vapor, detection of organic molecules or unusual isotope ratios. Enceladus makes this relatively easy. Its geysers spray ocean water into space where spacecraft can fly through and analyze it. Europa will be harder. Its ice shell is thicker, plumes less frequent, but still potentially detectable. Future missions will carry more sophisticated instruments. Europa Clipper, launching in the 2020s, will conduct dozens of close flybys, using ice-penetrating radar to map the ocean's depth and salinity, analyzing any plume material it encounters, measuring the thickness and structure of the ice shell. If conditions look promising, a follow-up mission might attempt to land, drill through the ice, and deploy a submarine into the ocean below. That mission is decades away, requiring technology that doesn't exist yet, but the concept drives current planning. The technical challenges are immense. Europa's radiation environment is lethal. Jupiter's powerful magnetic field traps charged particles that bombard the Moon's surface. Any lander would need heavy shielding, limiting how long it could operate. Drilling through potentially tens of kilometers of ice requires enormous energy, autonomous operation without real-time control from Earth, and mechanisms that can handle unknown ice compositions and temperatures. The submarine would need to function in complete darkness, navigate without GPS, avoid obstacles it can't see, and operate for months or years on limited power. These aren't problems that stop the mission, they're engineering challenges that get solved incrementally. Each generation of spacecraft pushes capabilities further. Perseverance on Mars carries instruments that earlier rovers couldn't have supported. Webb's mirror deployment, unfolding in space with terrifying precision, seemed impossible when first proposed. Technology advances, budgets fluctuate, but the trajectory points toward increasingly ambitious missions. Finding microbial life would answer one question while raising dozens more. How did it originate? Does it use DNA or something else? How does it metabolize? What's its evolutionary history? Is it related to Earth life, perhaps spread between planets by meteorite impacts, or did it arise independently? That last question matters enormously. One genesis of life in our solar system could be coincidence. Two independent origins would suggest life emerges readily when conditions permit, implying a universe full of biology. Panspermia, the idea that life spreads between worlds, has scientific support. Meteorite impacts can blast rocks into space, some eventually landing on other planets. We found Martian meteorites on Earth, rocks blasted off Mars by ancient impacts that drifted through space before falling here. The journey takes thousands to millions of years, but microbes can survive that, forming dormant spores that withstand radiation, vacuum, and extreme cold. If Earth life originated on Mars and spread here, or vice versa, finding Martian microbes might reveal them as distant cousins of terrestrial organisms, sharing the same genetic code and basic chemistry. Testing that hypothesis requires sequencing alien DNA, if it has DNA, comparing its structure to Earth life, looking for similarities too specific to arise independently. If Martian life uses the same 20 amino acids, the same 4 DNA bases, the same genetic code translating base sequences into proteins, common origin becomes likely. If it uses completely different molecules, independent origin is certain. The philosophical implications cut deep. Religions and philosophies have grappled with humanity's place in the universe for millennia. Finding alien life, even microbes, shifts those discussions fundamentally. We're not unique. Biology isn't a miracle exclusive to Earth. The universe makes life when given the chance. That realization could unify humanity around our shared biological heritage or fracture existing worldviews that place humans at creation's center. History suggests both reactions will occur simultaneously, different cultures and belief systems integrating the discovery in different ways. Science fiction imagined first contact as dramatic, flying saucers landing on the White House lawn, radio signals from distant civilizations. Reality will probably be subtler, a chemical signature in an exoplanet's atmosphere that takes years to confirm, a microscopic fossil in a Martian rock sample, organic molecules in Europa's ocean that match no known geological process. The discovery won't happen in a single moment but through accumulating evidence that gradually shifts scientific consensus. And what if we find nothing? What if Mars is sterile, Europa's ocean empty, Titan's lakes purely chemical? That answer matters too. It would suggest life requires specific conditions we haven't identified, that Earth's combination of factors is rarer than we thought. The galaxy might be full of potentially habitable worlds that remain lifeless because some crucial ingredient is missing. That wouldn't prove we're alone, the universe is too vast, but it would suggest loneliness is possible, that consciousness might be precious because it's rare. Current evidence leans toward optimism. Organic molecules appear everywhere we look, in comets, asteroids, interstellar clouds, even in the atmospheres of planets where they can't support life. The chemistry of life isn't exotic, it's common. Water, once thought rare, turns out to be abundant, locked in ice throughout the outer solar system, probably common around other stars. Energy sources exist anywhere geology stays active: tidal heating, radioactive decay, chemical gradients between different rock types. The ingredients are widespread. Whether those ingredients combine into biology remains unknown. Chemistry becoming life requires specific conditions we're still mapping. Temperature must fall within certain ranges. Too cold and reactions stop. Too hot and complex molecules break apart. Liquid solvent is necessary, probably water, though alternatives might work. Energy flow must be steady and sustained, not sporadic bursts. Concentration mechanisms need to exist, ways to accumulate organic molecules rather than letting them drift apart. Protection from radiation helps, thick atmospheres or deep waters shielding fragile chemistry from destructive high-energy particles. Earth had all those conditions simultaneously. Did Mars? Does Europa? The uncertainty drives exploration. Every mission returns data that refines our understanding, narrows the possibilities, points toward where life is most likely. Negative results inform as much as positive ones, each sterile world teaching us what conditions aren't sufficient, helping identify what additional factors matter. The timeline stretches across decades. Sample return from Mars won't happen until the 2030s. Europa exploration extends into the 2040s. Titan submarine missions, if they happen, lie further still. Breakthrough discoveries could accelerate everything. Finding clear biosignatures might trigger urgent follow-up missions with compressed timelines. Or progress might slow, budgets tighten, priorities shift, and the search extends across centuries rather than decades. What remains certain is that the search continues. Humans seem compelled to explore, to push boundaries, to answer fundamental questions about existence. Whether life exists elsewhere ranks among the most fundamental questions we can ask. The answer, whatever it is, reshapes how we understand our place in the cosmos. Finding life beyond Earth wouldn't just answer whether we're alone. It would fundamentally alter how we understand biology itself. Every organism we've studied shares the same basic architecture: DNA, RNA, proteins built from the same 20 amino acids, cells with similar structures. That's not because it's the only way to build life, but because everything alive today descends from a single origin point roughly 4 billion years ago. We've been studying variations on one theme, different arrangements of the same fundamental components. A second genesis would show us an entirely different approach to the problem of being alive. Consider what Martian life might teach us. If we find microbes in subsurface water, the first question becomes how similar are they to Earth organisms? If they use DNA, that's either remarkable convergence, the same solution emerging independently, or evidence of panspermia, life transferring between planets on meteorites. Mars and Earth have exchanged material constantly throughout their histories. Impacts blast rocks into space, some eventually falling onto the other planet. Microbes could survive that journey, protected inside rock from radiation and vacuum. If Martian life shares our genetic code, we'd need to determine whether Mars seeded Earth, Earth seeded Mars, or both were seeded from elsewhere. The implications multiply rapidly. But what if Martian biochemistry is completely different? Different genetic molecules, different amino acids, different cellular organization. That would prove life isn't locked into one configuration, that chemistry can solve the problem of self-replication and metabolism through multiple pathways. Every difference would reveal something fundamental about what life requires versus what's merely one option among many. Does all life need cells, or could some function as connected networks without clear boundaries? Must genetic information be stored in double helix structures, or would other shapes work? The variations would illuminate the core principles underlying all biology. Europa's ocean presents different possibilities. If life exists there, it evolved in darkness, powered entirely by chemical energy rather than sunlight. Earth has similar ecosystems around hydrothermal vents, entire communities thriving on chemicals rather than photosynthesis. But those ecosystems exist alongside photosynthetic life, sharing the same ocean, likely descending from the same origin. Europa's life, if it exists, would have developed independently in perpetual darkness, never knowing sunlight, possibly never developing anything resembling plants. The food chain would start with chemosynthetic microbes and build upward from there. How complex could such an ecosystem become without the energy abundance photosynthesis provides? The energy question matters enormously. Photosynthesis captures sunlight directly, providing massive energy input that drives Earth's biosphere. Chemical energy from geology offers far less, limiting how much biomass an ecosystem can support. Europa's ocean might contain only sparse microbial populations scattered around hydrothermal vents, nothing more complex because insufficient energy exists for larger organisms. Or perhaps life there discovered methods we haven't imagined, ways to extract energy more efficiently, to build complexity with less power. The possibility remains open until we explore. Titan raises even stranger questions. If life exists in liquid methane at -179 Celsius, it's operating on completely alien chemistry. Water-based biochemistry relies on specific properties, how water molecules interact, how they dissolve certain substances while excluding others, how they remain liquid across a temperature range suitable for complex reactions. Methane has different properties entirely. Life using methane as solvent would need different molecules, different reaction pathways, different cellular structures if it has cells at all. We can barely imagine what such organisms would resemble. They might not even be recognizable as life initially, their metabolism so slow and alien that distinguishing biology from geology requires years of study. Each potential discovery carries philosophical weight beyond the scientific. Confirming we're not alone eliminates one form of cosmic loneliness while potentially introducing another. If we find only microbes, simple organisms that never evolved complexity, we'd know life exists elsewhere but might still be alone as conscious beings. The galaxy could be full of bacterial worlds but empty of minds, civilizations, anyone to communicate with. That's simultaneously comforting and isolating, proof that Earth isn't unique in hosting life but confirmation that intelligence might be. The cultural impact would unfold gradually rather than explosively. Religious traditions would adapt as they always have when new information emerges. Some would see divine creation extending beyond Earth, life as something the universe was designed to produce abundantly. Others might view Earth as specially blessed, the only place where God's creation achieved consciousness. Most would probably integrate the discovery into existing frameworks without fundamental disruption. History shows humans are remarkably good at absorbing paradigm shifts while maintaining continuity with the past. Science would transform more dramatically. Astrobiology would shift from theoretical to empirical, from asking whether life exists elsewhere to studying how it works. New fields would emerge, comparative biochemistry examining different solutions to biological problems, xenobiology studying organisms with fundamentally different architecture, ecosystems analysis comparing Earth communities to alien ones. The questions multiply endlessly. How does evolution operate under different conditions? Do alien ecosystems show similar patterns of predator-prey relationships, symbiosis, competition? Does complexity emerge through similar stages everywhere or follow completely different paths? The practical applications might surprise us. Studying organisms adapted to extreme conditions often reveals useful chemistry. Enzymes that function in boiling water now enable DNA analysis techniques. Microbes that survive intense radiation inform medical treatments. Life from Europa might show us how to operate in low-energy environments, relevant for long-duration space missions. Titan organisms could teach us chemistry that works at extremely low temperatures, potentially revolutionizing refrigeration technology or cryogenics. You can't predict what studying alien biology might enable because the discoveries themselves are unpredictable. Search strategies continue evolving. Next-generation telescopes will examine exoplanet atmospheres in unprecedented detail, looking for chemical signatures that suggest biological activity. Oxygen combined with methane creates disequilibrium. The gases react and destroy each other unless something continuously produces them. On Earth, that something is life, photosynthesis making oxygen while bacteria produce methane. Finding that combination around distant stars would warrant intense scrutiny, though geological processes might create similar patterns without biology. The challenge lies in distinguishing life from clever geology across light years of distance. Sample return missions represent the gold standard, bringing material back to Earth where sophisticated laboratories can analyze it thoroughly. Mars sample return launches in the early 2030s, collecting rocks that might contain fossilized microbes or chemical traces of ancient life. Those samples will be studied for decades, examined by technologies that don't exist yet, potentially preserving evidence until analysis methods become sophisticated enough to detect what we currently miss. The same rocks might be reanalyzed by scientists in 2100 using techniques we can't imagine today. The timeline for discovery remains uncertain. It could happen next year, a Martian rover stumbling across clear biosignatures in an unexpected location. Or it might take centuries, requiring technology we haven't developed, missions to destinations we haven't reached. The search itself drives progress regardless of outcome. Building instruments sensitive enough to detect alien life requires advancing multiple technologies simultaneously, better sensors, more sophisticated analysis techniques, improved propulsion for reaching distant targets. Those advances benefit other fields, medical diagnostics, materials science, environmental monitoring. The search pays dividends even before finding anything. What happens if we discover not just life but intelligence? That possibility seems remote within our solar system. No evidence suggests conscious beings exist on Mars or Europa. But the galaxy contains billions of stars, billions of planets, vast distances we've barely begun exploring. If intelligent life exists, we might detect their signals, radio transmissions, or other electromagnetic evidence of technological civilization. Or perhaps they're quiet, either deliberately avoiding detection or simply not broadcasting. The space between stars is enormous, signals weaken with distance, making detection challenging even if civilizations exist. Contact with intelligent aliens would raise questions we can barely formulate. How do you communicate across species that evolved independently, with no shared reference points, possibly no common sensory experience? Mathematics might provide a starting point, universal patterns that any technological civilization would recognize. But moving beyond basic concepts to actual communication requires bridging gaps we've never encountered. Human languages evolve together, sharing deep structure even when superficially different. Alien languages might operate on completely different principles, perhaps not using sound at all, maybe based on chemical signals or visual patterns or something we haven't conceived. The discovery of any life beyond Earth, whether microbial or intelligent, simple or complex, would mark a threshold in human history. We'd become the species that learned we're not alone, that answered one of the oldest questions our ancestors asked while staring at stars. That knowledge changes how we see ourselves, our planet, our future. Earth stops being the only known living world and becomes one example among many. Our biology stops being the only known solution and becomes one variation on a theme that plays out across the cosmos. Right now, we exist in uncertainty, not knowing whether life is common or rare, whether the universe teems with biology or whether Earth represents a singular miracle. That uncertainty drives the search forward, propels missions to Mars and Europa and Titan, motivates scientists to keep looking, to keep testing, to keep pushing the boundaries of what we know. The answer waits somewhere in the data we haven't collected yet, in the samples we haven't analyzed, on the worlds we haven't explored. And every mission, every discovery, every new piece of evidence brings us closer to knowing whether we're alone or whether life, in all its strange and wonderful forms, fills the universe around us. The search for life beyond Earth isn't just about finding microbes in ice or detecting unusual gases in distant atmospheres. It's about understanding whether we're witnessing something unique or something inevitable. Every ocean world we study, every atmospheric anomaly we investigate, every chemical signature we can't explain adds weight to one side of that question. Ganymede orbits Jupiter exactly as it has for billions of years. Its ocean sloshes beneath ice that has remained frozen since the solar system's youth. The magnetic field deflects radiation. Tidal forces squeeze the interior rhythmically. None of this changes whether we look or not. The moon exists independent of our curiosity. But we look anyway because understanding Ganymede means understanding how common habitable environments might be throughout the galaxy. The missions we're planning won't answer everything. Europa Clipper will map the ice shell and search for plumes but won't drill through to the ocean. JUICE will orbit Ganymede and measure its gravitational field but won't deploy submarines into the depths. These are reconnaissance missions, gathering data that will inform what comes next. They'll tell us where the ice is thinnest, where tidal heating concentrates, where future landers should aim. They're setting the stage for something more ambitious, missions that actually touch these frozen surfaces and taste the oceans below. That next generation of exploration lies decades away. The technology needs refinement. The funding requires political will that fluctuates with election cycles. The engineering challenges demand solutions we're still developing. But the trajectory is clear. We're moving from observation to investigation, from studying these worlds from afar to directly sampling what they hide. Whether Ganymede harbors life remains unknown. The ocean exists, that's confirmed. Whether chemistry there crossed the threshold into biology depends on factors we're still mapping. But the possibility alone justifies the search. If life arose independently in Jupiter's system, if organisms exist that never saw sunlight, that evolved in darkness powered by tidal forces and chemical gradients, then the universe becomes fundamentally different than we imagined. Life stops being Earth's miracle and becomes the cosmos doing what it does when conditions align. And if we find nothing, if Ganymede's ocean proves sterile despite billions of years and all the necessary ingredients, that answer teaches us something too. It reveals that liquid water and chemical energy aren't sufficient, that life requires additional factors we haven't identified. The search continues either way, moving to Europa, to Enceladus, to Titan, to exoplanets around distant stars. Each investigation refines our understanding, narrows the possibilities, points toward where life is most likely. The answer exists whether we find it or not. Somewhere in the frozen depths of Ganymede, or the radiation-blasted ice of Europa, or the methane lakes of Titan, or the atmospheres of worlds we haven't reached yet, the universe has already decided whether biology emerges readily or remains vanishingly rare. Our searching doesn't change that reality. It only determines when we learn what's already true.